Building boats has been a part of society's traditions for years. From the moment that we learned of the endless resources that the waters of the earth hold, we have been building boats. Though the original boats were built of different types of woods from trees in the surrounding areas, modern-day boat building can be seen being done with cardboard. Whether building these cardboard boats are done recreationally or even for friendly competitions, the art of cardboard boat building is slowly becoming popular. Besides the fun and competition, building cardboard boats can also serve as a cost-efficient way to change the way we build actual boats. Now, the things that need to be considered when making a boat are the cost efficiency, of course, how long it can stay on the surface, and how far it can travel. Although cardboard boats are not used for the same purposes, they can still be used as examples for designs that will increase the efficiency of boats that have more important jobs. Which brought my research team and I to the question, what geometric base would go the furthest before sinking, stay above water the longest, and be the most cost-efficient? Our hypothesis was that if you have a single person enter and row 3 different types of boat bases, a trapezoid, parallelogram, and rhombus, then the boat with the rhombus base would be able to go the furthest and hold the individual the longest. This hypothesis can be drawn because shape-wise, the rhombus boat is more likely to cut through water, allowing it to go at a faster pace. As for how long the boat can carry the individual, the rhombus boat will hold the longest because the weight of the individual will be more spread out. Then it was time to test this out. The materials that we used to make the boats were 1 meter stick, 1 protractor, some graph paper, cardboard, approximately 3 boxes, rope or twine, tape, you want about 4 or 5 rolls, paint, preferably spray paint, a pool to test the boats in, and a tape measure. How did we build and test these boats? It wasn't easy. First, our research team of 6 split into 3 groups, and each group was assigned a boat to build. How the boats were built was up to the imagination of the constructors. The pair in charge of the rectangular boat decided to use heavy-duty duct tape and put most of it on the bottom and at the seams of the boat. Whereas the pair in charge of the rhombus boat decided to tape all of the boat all the way around and reinforce the edges. Those who built the trapezoid did a mixture of the two. They put a lot of tape on the front of their boat and a bit on the bottom as well. The way the boat is designed is truly up to the builders, but it is a factor that has been taken into consideration in the end. Now for the actual experiment. To do this, the first step after building the boat, of course, is to place one of the boats inside the shallow end of the pool so that the individual can get in. Note that the boat will be going widthwise and not lengthwise. You'll want to set up a tape measure on the outside of the pool beforehand. As soon as the individual is ready, start a timer and ask the individuals to begin rowing themselves across the pool. Next, we had one person record how long it took until the boat sank, and the other person recorded how far the boat was able to go. Then we repeated this for the next 2 boats. In the end, going back to the hypothesis, we can see that our prediction was not correct. However, there were other variables coming into play aside from the shapes. A few shortcomings of the investigation were the size of the boats. They varied greatly. The trapezoid was the smallest and had the lowest walls, which caused the boat to leak much quicker than the others, while the rhombus was the largest and had walls that were difficult to work around. In addition to this, all 3 boats were insecure in their joints, which caused them to sink rather quickly due to the amount of water flooding in. The rhombus had a quite delicate base, as the cardboard was the flimsiest and there wasn't as much tape on the bottom. As for the trapezoid, the walls were drastically uneven. One side was considerably higher than the other. The short wall was also insecure and fell through once the water started flooding in from the joints. A further study could research what material works best for floatability and how the size of the boat affects the result. Wood would most likely be the best material for boat building as its density is less than water's and it stays cooler than other materials such as aluminum and composite in the sun. A longer boat would move faster because it would cut through the water more easily. The longer the boat, the higher the hull speed. If another study was to be done, it might be interesting to research what material works the best for floatability. But from this particular investigation, we were able to conclude that the best boat shape depends on the purpose of the boat. If a person is looking to make a cost-efficient boat, then the best boat shape would have been the trapezoid. But if a person just wants the boat to float, then the rhombus would have been the best. Seeing as a good amount of boat manufacturers want their boats to go a distance as well as float for a long time, then it would be a matter of combining the technique used to build the rhombus boat, but then also use the rectangular shape.